In question number 15, there's one important point that one must understand at the very beginning. Let's say that that rectangle is the elevator, and let's say that this is the person who is standing on a weighing machine. Maybe it's over here. Now the elevator may be moving up or it may be moving down, whatever it is. But one point to take note of is that the reading of the weighing machine in general is not going to be equal to the true weight mg of the person. It may be sometimes equal to mg, but in general you can't say that it's going to be equal to mg. Now the question remains, what then is the reading of the weighing machine? So if you look at the figure, you realize that the weighing machine is going to experience a force because of the person's feet, and that's nothing but the normal reaction exerted by the feet of the person on the weighing machine. It is this normal reaction, that is the force exerted by the feet of the person on the weighing machine, which the weighing machine shows as the weight of the person. In other words, the weight of the person as measured by the weighing machine is not the true weight, but we could call it the apparent weight. Now let's read ahead in the problem. The problem says that the maximum weight recorded by the machine. Now of course it means the maximum apparent weight as discussed earlier. So the maximum apparent weight as recorded by the weighing machine is given to be 72 kilograms. Now this is slightly questionable, this kilograms, because as you know, weight is a force and kilogram is the unit of mass. So to understand this issue, you must understand that a normal weighing machine would be calibrated in kilograms. So for example, if a mass of 1 kilogram is put on top of a weighing machine like that, and the weighing machine is placed on the ground, then the weighing machine would read or it would show a mass or a weight of 1 kilogram, because that's the way the scale is calibrated. But in reality, the weight which is being measured by the weighing machine is 1 kilogram multiplied by g, which is 9.8 meters per second square. So that's the conversion actually. When the question says that the maximum apparent weight as recorded by the weighing machine is 72 kg, what is meant is 72 multiplied by 9.8 newtons is the maximum apparent weight, and likewise the minimum apparent weight recorded by the weighing machine is given to be 60 kilograms, but obviously it's actually 60 multiplied by 9.8 newtons. Of course, in the question it is mentioned that the value of g to be taken is 9.9 meters per second square. So actually what I should have written here is 9.9, and likewise 72 kg corresponds to 72 into 9.9 newtons, and 60 kg corresponds to 60 into 9.9 newtons, but that's a minor point. Now let's try to write the data given in the problem. The motion of the elevator has three distinct phases. In the first phase, the elevator is moving upwards with some positive acceleration a. In the second phase of motion, the elevator moves upwards with a uniform velocity. And finally, in the third phase of motion, the elevator decelerates to a stop, but the magnitude of the deceleration is the same as the magnitude of the acceleration during the first phase. And this essentially means that in the third phase of motion, the elevator moves upwards with an acceleration of a in the downward direction. Now the question actually asks us in part B the magnitude of the acceleration. In other words, part B asks us this question, and part A asks us the true weight of the person. And the true weight of the person would be the person's mass times the gravitational acceleration. Indirectly, we have to find what is the mass of the person. To solve the question, let's try to analyze the different phases of the motion separately. Let's begin with the first phase of the motion when the acceleration is a in the upward direction. So in this physical diagram, I'll actually show the acceleration upwards a, and now essentially we are going to apply Newton's second law of motion to the man. But we have two options in front of us. We can analyze the whole situation from the ground frame. So maybe let's imagine that this is the ground. So this is an inertial reference frame, and we can of course apply F is equal to ma to the man, and we can solve the problem in the ground frame completely. The second option is to solve the problem in the elevator frame. So we go to the reference frame, we attach a reference frame to the elevator, we go to that reference frame, and we apply Newton's second law of motion once again to the man. But when we do that, we must note one very important point, namely that the elevator frame is a non-inertial reference frame because it has an acceleration with respect to the ground. And that means when we apply Newton's second law of motion to the man, we must necessarily incorporate pseudo forces, if any. Now we will solve the problem in the reference frame of the elevator, although in this particular problem it is equally easy to solve it in the reference frame of the ground. So I begin by drawing the FBD of the man, but this FBD, one must remember, is in the frame of reference of the elevator. So let's see, the man is over here like that, and the forces acting on the man. The first very obvious force is the man's true weight, m times g. The second force is the normal reaction N1, which is exerted by the elevator on the feet of the man. And this force N1 is actually the apparent weight as discussed earlier. Now, the third and final force is the pseudo force. And as we know, this pseudo force is related to the acceleration of the elevator in the ground frame. The acceleration is a in the upward direction, and so the pseudo force is obtained by drawing an arrow in the downward direction and assigning a magnitude to the pseudo force of the mass of the object. In this case it's the man, multiplied by A. So we have covered all the three forces acting on the man in the elevator frame. Two of the forces, that is mg and the normal reaction, are real forces, and the third force is a pseudo force. Now we proceed to apply Newton's second law to the man, namely sigma F is equal to mass times acceleration in the elevator frame. But remember, in the elevator frame the man is at rest, so sigma F must be equal to 0. And so when we apply sigma F is equal to 0, let's say in the upward direction, what we get is N1 upward force minus mg, because mg is the downward force, minus m times a equal to 0. And since we want this equation to be used, we want to use it later on, I just transfer the equation to a safe place over here, and I call it equation number 1. And now I just rub out all of this stuff which is unneeded, and we now draw the FBD of the man once again in the frame of reference of the elevator, but this time we do it in the third phase of the motion, that is when the elevator is moving up with deceleration. Now in the diagram, in the physical diagram, the acceleration of the elevator is still a, but now the direction has reversed, so this arrow must point in the downward direction. So that's the physical diagram. Now when I draw the FBD of the man in the elevator frame, I'll just show the man like that. And of course the first force, very obvious force acting on the man, is mg, his true weight in the downward direction. The other force acting on him is N2, the normal reaction exerted by the weighing machine on the man's feet, and it's not equal to N1. There is no reason for us to believe that N1 is equal to N2, so I assign an altogether different symbol, N2. And in this case, when the elevator is accelerating downwards, the pseudo force is going to be in the upward direction. And in the elevator frame, obviously sigma F is equal to 0 as before, and so I'll write my equation just below equation number 1. Sigma F is equal to 0 in the vertically upward direction implies that N2 minus mg plus ma is equal to 0. That's my equation number 2. Now, do you remember that in the question it is stated that 72 multiplied by g, in this case 9.9 newtons, is the maximum apparent weight of the man, and 60 into 9.9 newtons is the minimum apparent weight of the man. Of course, when we say apparent weight, we are talking about the normal reaction exerted by the weighing machine on the man. So 72 into 9.9 newtons is the maximum normal reaction, and 60 into 9.9 newtons is the minimum normal reaction. Now in the diagram, in the FBD which has been drawn here, clearly the pseudo force which is in the upward direction is helping N2 to balance mg. In other words, N2 can afford to be small because MA is helping it, and that's why N2 is going to be the minimum normal reaction during the entire motion. And so what I'll do is to substitute for N2 in equation number 2. In place of N2, I'm going to write 60 multiplied by 9.9 newtons. On the other hand, in the first phase of the motion, when the elevator is accelerating upwards, the pseudo force MA is in the downward direction as discussed earlier, and the normal reaction then is called N1. In this case, N1 is balancing the sum of mg and ma, and obviously N1 has to be large, and so N1 is going to be the maximum normal reaction given in the question, which is 72 into 9.9 newtons. And so when I look at equation number 1, I realize that I have to substitute in place of N1. I'll write 72 into 9.9 newtons. So let me write these two equations, one below the other, in their final forms. Equation number 1 is 72 into 9.9 minus the mass of the man is unknown, m, multiplied by g is to be taken as 9.9 meters per second square minus m times a, that's equal to 0. This is equation number 3. Likewise, equation number 2 finally becomes 60 multiplied by 9.9 minus m into 9.9 plus m into a is equal to 0. That's equation number 4. And you'll notice that in these two equations there are two unknowns, m, which appears in several places, and the other unknown is a. And because there are only two unknowns, I can solve two simultaneous equations to find these two unknowns. So you can solve them, and finally you will get an answer for m, and m turns out to be 66 kilograms. And when we find the answer for a, it turns out to be 0.9 meters per second square. And these are the two answers which we are seeking. Note that in part A, we have been asked to find the true weight of the man. So that means that if we use the proper units, it should be 66 multiplied by 9.9 newtons. But since the scale of the weighing machine is calibrated in kilograms rather than in newtons, we express the answer as 66 kilograms. That is, the true weight of the man is equal to 66 kilograms. If you are still uncomfortable with the fact that we are using a unit of mass to express the weight, then you could treat kilogram as kilogram force. So the true weight of the man is 66 kilogram force, and the magnitude of the acceleration is 0.9 meters per second square.